Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section P5 on factoring polynomials. So there's really only one type of problem in this section, and that is, of course, factoring polynomials, but we're going to cover many different methods for how to accomplish that goal. And some of the methods we're going to see are greatest common factor, something called factoring by grouping, which only works under certain circumstances, the general formulas for factoring quadratic polynomials, ax squared plus bx plus c. We're going to take a look at some special products that we have formulas for. Those are a difference of perfect squares and sums and difference of perfect cubes. And then we're also going to have a method called substitution, where you can take something that maybe looks more complicated and break it down into the same methods that we use to factor quadratic polynomials. And of course, you're also going to have some polynomials that combine multiple of these methods together. So each method works best under certain circumstances. So let's go ahead and get started with our first method, the greatest common factor method. So the greatest common factor method is pretty much exactly that. If you have a common factor between several or all of the terms in your polynomial, then you can factor it out of those terms. This is usually your go-to first step anytime you see you have a common term in every part of your polynomial. So in example 1, if we take a look at part A, we've got 9x to the fourth minus 6x cubed plus 12x squared. There are factors in common between all three of these terms. All of the numbers, for example, are divisible by 3, and all of the x's are divisible by x squared. There's an x squared in common between all three. So we can factor a 3x squared out of all three terms. Factoring is the same as division, so just think about what's left over after you pull that out. If you factor a 3x squared out of 9x to the fourth, you're left with another 3x squared. If you pull a 3x squared out of 6x cubed, that would leave you with a 2. You pull out 2 of the 3x's, x to the first power. And if you pull a 3x squared out of 12x squared, you've removed all of the x's, but you're still left with a factor of 4. You can always double check yourself after factoring by thinking about what would happen if you redistributed or remultiplied the polynomials together. It should always take you back to where you started, which it would in this case. For part P, we've got more terms floating around. We've got constants, we've got x's, and we've got y's. So remember, we've got to have something in common between all terms in order for this greatest common factor method to work out the way we want it to. So take it a piece at a time. Think about the constants, think about the x's, think about the y's. So for the constants, we've got an implied coefficient of 1 in the first term, a 10, and a 25. Now, definitely a common factor between the 10 and the 25, but the fact that there's nothing in this first term, that kind of ruins that. So there's no constant you can pull out of all three. For x's, you've got an x squared and an x in the first two. They have stuff in common, but there's no x in the third term. So no power of x in common between all three either. So our last chance is y, and what we've got in this case is that there is a y to the first power in all three. So if we pull that out, the first term would just have the x squared left over. The second term would just have the 10x left over. And the final term would just have the constant of 25. Now you might kind of see where this is headed in future parts of the section. This thing that we're left with in parentheses now can actually factor further, though we haven't gotten there yet. For now, we are just asked to factor out the greatest common factor, so this is where it is. But that does illustrate one of the uses of the greatest common factor method, is that oftentimes it's the first step of factoring a larger polynomial completely. Next up, we've got our second method, factor by grouping, and this method really only works under very specific circumstances. It just turns out that those circumstances pop up a lot, and we'll talk more about that when we get to factoring ax squared plus bx plus c in a bit. So the idea between factor by grouping is this. If you've got a 4-term polynomial, if you see that you've got stuff in common between pairs of the terms, try doing the greatest common factor method between the pairs. And so let's start with an example, part A. So there is nothing in common between all four terms. There's nothing you could pull out of all four. But between the first two, you have an x squared that you could pull out, which would leave you with x to the first power, and then a 1. Be careful. Anytime you factor an x squared out of itself, because remember, factoring is division, that doesn't make it go away completely. That doesn't give you a 0. That does leave you with a 1 left over. Imagine redistributing it through. Make sure it goes back to where it came from. For our second pair of terms, we've got a 3 in common between the two. So we've got a plus in between. If I factor a 3 out of both terms, that would leave me with an x for the first, and again, 3 divided by 3 would leave me with the 1 for the second. Now the idea between factor by grouping is that if you perform this process and then you see you ended up with the same thing in both parts, you can do the greatest common factor method again. Now we have a 2-term polynomial, and both of these have a common factor of this x plus 1 in parentheses. So if I factor that x plus 1 out of both terms, we're left with the x squared from the first term and the plus 3 from the second term. Right? And so that x plus 1 came out front, which is why now there's only one of them. And so that polynomial would factor to x plus 1 times x squared plus 3. Part B is the same kind of problem, but it illustrates an important point, and that's that sometimes you need to rearrange the terms in order to accomplish your goal. So if you take a look at the first two terms this time around, there's nothing in common between the two. AW in the first, BC in the second. Same for the last two sets of terms. But the first and last term has an A in common, and the middle two terms have a B in common. So what if we rearrange things a little bit? I'm going to move that AC a little bit higher up in the problem. So this is going to be AW, the minus sign travels with it, minus AC plus BC minus BW. And now let's see if we can do factor by grouping. So if we pull an A out of the first two terms, we're left with W minus C left over. And if we factor a B out of the second two terms, we're left with C minus W. Now this is not quite right. W minus C, C minus W are not the same thing. Now if that was addition, you could just swap the order of the terms. W plus C is the same as C plus W. Addition is commutative. That's not the case with subtraction though. So instead what we need to do whenever we have something that looks like this, you've got two terms subtracted but in the reverse order, is you need to factor out a negative 1. So think about that. If we have W minus C and we pull a negative 1 out of both terms, that's like dividing by negative 1. It changes the sign of each term in the problem. And negative W plus C is the same as C minus W. So you can swap the order of the subtraction by pulling out a negative sign. So that's what I'm going to do here. I could actually pull it out of either term, it doesn't matter. I'm just going to go ahead and pull it out of the second. And when I pull that minus 1 out, I'm just going to go ahead and use that to change the plus in the middle into a minus. And so now we meet the conditions for the second step. We've got a W minus C in common. So if we pull that out, we're left with the A from the first term and the minus B from the second. So now let's talk about the type of factoring that most people kind of first think of when they hear the word factoring, and that's factoring specifically quadratic polynomials, something of the form ax squared plus bx plus c. So I'm going to show you guys a really procedural approach to factoring this type of problem, and the problem gets exponentially more difficult if there is actually a coefficient of the x squared. That's what makes the problem a little bit tougher. So what I'm going to show you is something called the British method for factoring a quadratic polynomial. The idea is you're looking for two numbers who add up to give you what is called the linear coefficient, the coefficient of the x to the first power, b, and whose product, if you multiply them together, gives you a times c, the quadratic coefficient times the constant term. Once you find those two numbers, you use those to break up the bx term in the middle into two pieces, using the numbers that you just found. And it turns out that if you take that approach, if you can find those two numbers, it always sets it up so that you can then factor by grouping, the method that we just talked about on the previous slide. So let's take a look at some examples involving the British method. All right, so in example 3, part A, we're asked to factor the quadratic polynomial 15x squared minus 14x plus 3. So if we use the British method here, our goal is to find two numbers that add up, whose sum is the number in the middle, negative 14, the coefficient of x, and whose product is a times c, 15 times 3, or 45 in this case. Now, the sign of the product can tell you whether you're looking for, or it can help clue you into the signs of the numbers you're looking for. So since our product is positive in this case, positive 45, the only way that happens is if you multiply two positive numbers together, that would give you a positive, or if you multiply two negative numbers together. So in other words, the signs have to be the same. If you multiplied a positive times a negative, we would have a negative product instead. So the signs are the same. They're either both positive or both negative. But because we also know they have to add up to give us a negative number, that tells us that we're looking for two negative numbers. It's the only way we could get this particular combination. All right, and then it's just about trying to figure out two things that multiply to give you 45 and add to give you 14. So you might try writing out some of the things, some of the integers that would multiply to give you 45, and just start doing a list and see if you can find two numbers. In this case, you would find that 9 and 5 are what you're looking for. Negative 9 times negative 5 would give you a positive 45. Negative 9 plus a negative 5 will give you a negative 14. So what I'm going to do is I'm going to break that minus 14x in the middle up into two pieces. So the 15x squared just carries down. But now I'm going to have a minus 5x and a minus 9x. Now, I'm going to be careful with the way I put these. I'm going to line them up so that they have factors in common with the stuff on the outside, just to save me a rearrangement step in a minute. Because this is a 15 out front, that seems to line up pretty nicely with the 5 at the end. So I'm going to put the minus 5x first, and then the minus 9 matches up with the 3 nicely. So I'm going to put the minus 9x second. The plus 3 carries down as well. Right? And so again, all we've done is taken that middle term and broken it up into two pieces. Hopefully we can all agree that if you recombine those two pieces in the middle together, minus 5x minus 9x, that would take you back to the minus 14x that it came from. And then from here, it's just factor by grouping. It's just a problem from the previous page. So for the first two terms, we've got a 5x in common. So if I pull a 5x out, that leaves me with 3x in the first term and a minus 1 in the second term. And then for the second two terms, we've got a 3 in common, but pay attention to what happens if I pull out a 3. That would leave you with a minus 3x plus 1, but I want that to match up with this 3x minus 1. So instead of factoring out a positive 3, I'm going to factor out a negative 3 to change the signs. That would give me a positive 3x and a minus 1. Now we pull out the common factor again, 3x minus 1, which would leave us with 5x for the first term, minus 3 for the second term. And so 15x squared minus 14x plus 3 would factor into 3x minus 1 times 5x minus 3. So try pausing here and see if you can use the same method to figure out the way that part B in this problem factors. All right, so similar concept. I'm looking for two things that add to give me the x coefficient of 5 and that multiply to give me a times c, 2 times 2, or 4 in this case. The product is positive again, so signs are the same. And if they add up to a positive number, I'm looking for two positive numbers this time around. Two things that multiply to give 4 and add to give 5 would be a positive 4 and a positive 1. So I'm going to break it up. The 2x squared comes down. The 5x is going to become 4x plus 1x. And then the plus 2 carries down as well. Factor by grouping. If I pull a 2x out of the first two terms, that will leave me with x plus 2. And the second terms are already x plus 2. So what I can do in order to put it in parentheses is factor a 1 out of both terms. That doesn't change anything. And then if I factor out the x plus 2 in common, we would be left with 2x from the first term and a plus 1 from the second. All right, so this method seems like it takes a long time in the beginning, but once you get used to it, you can factor polynomials very quickly this way. Another thing to note, guess and check is a valid way of factoring, but honestly, it could go either way. You could get lucky and guess the correct way to factor the first time around, or it could end up taking you a long time. So it's not really advised that you rely on that as your only way of factoring, because if you have a test problem like 15x squared minus 14x plus 3, you don't really want to spend 10 minutes trying to guess at how that factors out. Let's take a look at two more, and you'll notice something special about both of these, and that there's no coefficient in front of the first term, the quadratic term, anymore. And so that's actually going to simplify the method quite a bit. And this is the first type of factoring a lot of people learn when they're talking about quadratic equations, although this is really just a special case of the British method. So for the first problem, part C, I'm going to do the full method that we did on the previous page, and then we'll see what it eventually simplifies into. So for x squared minus 4x minus 12, I'm looking for two numbers whose sum is the minus 4 from in front of the x, and whose product is a times c, but since a is 1 in this case, it's just c. So whose product is negative 12. And so because the product is negative this time, that means the signs are different. We have a positive and a negative. And so that means this time around I'm looking for two things that multiply to give 12 and subtract to give 4. So that would be a 6 and a 2, but because the 4 is negative, I want my bigger number of 6 to be negative and my smaller number of 2 to be positive. So double check, multiply those together, you get negative 12. Add them, you get negative 4. So I'm gonna break it up. So we've got x squared. This is now going to be a plus 2x minus 6x minus 12. Then if we do the factoring by grouping like before, all we've got in common between the first two terms is x. So if we pull that out, we're left with x plus 2. And between the second two terms, I'm going to factor out a minus 6, which would also leave me with x plus 2. And then if I factor out the x plus 2 in common, that would leave me with x plus 2 times x minus 6. And so what you'll notice here is that those two numbers that we found, whose sum was the coefficient of x, b, and whose product was the constant term c, they just ended up being next to the x in our final answer. And that's actually always the case when you are working with a polynomial that has no coefficient in front of the x squared. So you can actually skip this step in the middle of breaking the term up and doing factor by grouping. Once you find your two terms, you can jump straight to the factored form in this special case. So let's try that out with part D. So this time around, we're looking for two numbers whose sum is positive 3 and whose product is negative 18. So again, the product is negative, so we got different signs. I'm looking for two things that would multiply to give me 18 and subtract, because the signs are different, to give me 3. So those would be 6 and 3, but this time I want the final sum to be positive. So I want my bigger number of 6 to be positive and my smaller number of 3 to be negative. Double check. 6 times negative 3 is a negative 18. 6 minus 3 would be a positive 3. So we can jump straight to the final answer. And my variable is y this time around, so don't write x. We would have y plus 6 times y minus 3. Anytime you factor using this method, it's a good idea to FOIL this back out, at the very least in your head, which you can do with a little bit of practice, and make sure that it does go back to what you started with. Right? It's always a shame to miss a test question just because you factor in a rush and you end up writing down the wrong factors. So double check yourself when you factor. Now, a lot of times when you're factoring polynomials, you combine methods together, and we'll take a look at a little bit more of this a little bit later on. But for now, let's take a look at a few that combine the methods we've covered so far. So starting with part A, where we've got 3w cubed minus 3w squared minus 18w, this is, at least in the beginning, a greatest common factor problem. Clearly all of the numbers are divisible by 3, and there's at least one w in all three terms. So if we pull a 3w out of each, that would just leave us with two w's, or w squared in the first, minus, we factored out the 3 and one of the w's, so there's just one left over, minus, if we pull an 18 out of this one, that would leave us with 6, and the w is gone now. But now, we've got, in parentheses, a quadratic polynomial that factors further. So we would be looking for, if we wanted to factor this, two numbers that add up to the coefficient of the first power term, or a minus 1 in this case, and that multiply, because there's no coefficient in front of the w squared, to give us negative 6. And so two things that multiply to give 6, the product's negative, so the signs are different. And subtract to give 1 would be 3 and 2. But because the sum is negative 1, I want the bigger number to be negative. Double check. Those multiply to give negative 6. Those add to give negative 1. Checks out. So we still got the w, 3w out front, but now this quadratic in parentheses will factor further into w plus 2 times w minus 3. Similar idea for part B. There is no variable in common between the three this time around because we have a constant without any x's, but all three of these numbers are divisible by 3. So I can factor a 3 out, but because I prefer my x squared term when I'm factoring to be positive, generally speaking, I'm actually going to factor a negative 3 out just to adjust that. You don't have to, it's just my personal preference. And that would leave us with a positive 2x squared, because all of the signs are changing since I pulled out the minus sign, plus 3x, and then that becomes a minus 14. This one takes a little bit more work to factor because, of course, there is still something in front of the x squared. So I'm going to do the full factor by grouping thing. So I'm looking for two things that add to give 3, the coefficient of the x, and that multiply to give us a times c, 2 times negative 14, a negative 28. Product is negative, so different signs. And if you hunt through the factors for 28, you'll find pretty quickly that you're looking for a plus 7 and a minus 4. All right, so I'm going to do a little bit of scratch work out to the side. I'm not going to forget that that minus 3 is still there at the end. So this 2x squared plus 3x minus 14 in parentheses, I'm going to break it up. Let's see what fits best where. The 4 probably goes best with the 2, and the 7 probably goes best with the 14. So I'm going to put the 4 first. That's going to be a minus 4x plus 7x minus 14. Pull a 2x out of the first two terms. Pull a 7 out of the second two terms. Pull an x minus 2 out of both. And so what we have then is a negative 3 times this factored form of the parentheses times x minus 2 times 2x plus 7. Next up, we've got some types of polynomials that pop up often enough that it's probably best not to factor them manually each time. We have formulas for them, although you could factor them manually, some with a little bit more work than others. And so these are difference of perfect squares and sums and difference of perfect cubes. So if you have a difference of perfect squares, something of the form a squared minus b squared, that will always factor into a plus b times a minus b. And because multiplication is commutative, if you do a minus b times a plus b, that also works. You basically just have to remember that the signs flip. And this is kind of the reverse of the multiplying of conjugates we were talking about earlier. You can double check this pretty easily. If you FOILed this out, you would get a squared, and then the minus ab and plus ab would cancel, and then you would get a minus b squared. All right, so that's definitely one to remember. It pops up very often. We've also got formulas for both the difference and the sum of perfect cubes. And these formulas are a little bit messier, so I'm going to explain to you the way I remember them. The first is that you'll notice that the pattern of the a's and b's are the same in both formulas. It goes a, b in parentheses, then it's a squared, ab, b squared. A, b, a squared, ab, b squared. The only thing that differs between the two formulas is the signs between the terms. In a cubed minus b cubed, it's minus plus plus. In a cubed plus b cubed, it's plus minus plus. And the way we remember that is with the word SOAP. Right? SOAP. It stands for same because the first sign is always the same as what's between your perfect cubes. The O in SOAP stands for opposite because the second sign always flips from the first. And then the AP for the final sign stands for always positive. Because the final sign is always a plus no matter what. Same, opposite, always positive. SOAP. So if you've got a cubed minus b cubed, same, minus, opposite, plus, always positive, plus. Now you will notice that there is no formula for a squared plus b squared here, and that's because a sum of perfect squares doesn't factor. So let's take a look at some problems involving these special product formulas. The first one's pretty straightforward. We've got x squared minus 16. The trick is to recognize that 16 is 4 squared, so that's a difference of perfect squares. So that's going to factor into x plus 4 times x minus 4. You could write that as x squared plus 0x minus 16 and factor it manually using the methods we talked about earlier, but again, you really don't want to have to do that every time because these difference of perfect squares pop up pretty frequently. Next up, we've got 2a to the fourth minus 32. So this doesn't immediately fit with any of our formulas, but there are a couple of tricks we can use to make it fit. The first is to recognize that there's a common factor between these two terms. You're supposed to start off this problem with the greatest common factor method. If you factor a 2 out of both, that would leave you with a to the fourth minus 16. Well, we just worked a problem with a minus 16. That's definitely a perfect square, but what about a to the fourth? Well, the trick is to recognize that because of properties of exponents, a to the fourth can be thought of as a squared squared. So this in fact is a difference of perfect squares. This is a squared squared minus 4 squared. And so if you factor it using the formula, first term plus the second, so it would be a squared, because that's what's being squared this time around, plus 4 times a squared minus 4. And once again, please remember that you can always just FOIL this back out, multiply it, and double check that it goes back to where you come from to make sure that you applied the formula correctly. Last but not least, we've got x cubed minus 27. And because 27 is 3 cubed, this is a difference of perfect cubes. Right? And so the formula goes like this. First term, a from the formula, x. Second term, 3. Then it's the first term squared, x squared. AB, so the product of the two, 3x. Then the second term squared, 3 squared, or 9. So that's what we see here. This is the AB, a squared, AB, b squared. And then for the signs, it's SOAP. Same, so a minus. Opposite, so a plus. Always positive. Plus again. The last type of method we're going to take a look at is called factoring by substitution. And the idea is that if you have something that looks like you can be thinking of it like a quadratic, so if u is any algebraic expression, not necessarily just a single variable, and you have something of the form au squared plus bu plus c, then you can still factor it like a quadratic polynomial, even if it's not just a single variable. Oftentimes we'll do a substitution to make it easier to see how it's factored, which is why it's called factoring by substitution. So let's take a look at a few examples involving factoring by substitution. So you can really see the power of this method in example 6 here, when you have something that looks like what we've got, especially in parts A and B, where you've got w squared plus 1 quantity squared minus 3 times w squared plus 1 minus 18. Now, a lot of students, when I ask them to factor something like this, they'll try to multiply everything out. So they'll square w squared plus 1, they'll distribute the minus 3 through. That makes the problem so much harder. Don't do that. This is some expression squared, some expression again to the first power, constant term. This looks like a quadratic. All you have to do is push it over the edge. So what we're going to do is we're going to make a substitution to make it easier to see. And the letter we usually use for substitutions is U, but you can honestly use whatever letter you want to. So let's let U stand for the term that is showing up and then showing up again squared. So in this case, U is going to be the w squared plus 1. Then this would become U squared. The second term would become minus 3u. And then the last term is a minus 18. It now looks exactly like a quadratic polynomial. And so we can factor it the same way we did before. We're looking for two numbers that add to give a negative 3 and multiply to give a negative 18. That would be a minus 6 and a plus 3. But be careful, we're not done yet. We don't want to leave our final answer in terms of u because u was just a temporary placeholder. Once you factor, you reverse your substitution. We started by replacing w squared plus 1 with u. Now we're going to replace u with w squared plus 1. So this becomes w squared plus 1, but you still got the minus 6. And this becomes w squared plus 1 plus 3. And then last but not least, you can now combine the like terms. So that first parentheses becomes w squared minus 5. And the second one becomes w squared plus 4. So try taking a similar approach to part B and see if you can factor this polynomial completely. Pause the video here. Okay, so again, this is one that's relatively easy to spot. We're going to let our u be the a squared minus 3. So this becomes u squared plus 7u plus 12. Which would factor into u plus 4 times u plus 3. So if we reverse our substitution now, that's an a squared minus 3 plus 4 and an a squared minus 3 plus 3, which would be an a squared plus 1. And then the minus 3 and the plus 3 just cancel each other out, so that would just be times a squared. And then last but not least, we've got part C. This one again might be a little bit trickier to see, but the key again is to remember by property of exponents that w to the fourth power is w squared squared. So we have a w squared here, and we have a w squared squared here. So if we let u be w squared, this would become u squared minus 6u minus 16. That would factor into a u minus 8 times u plus 2. Just to quickly double check myself, u squared minus 8 plus 2 would be a minus 6u minus 16. Checks out. And then I'm just going to reverse my substitution. U was w squared. So this is a w squared minus 8 times a w squared plus 2. All right, so that is it for the type of factoring methods that we cover here in section P5. Our last example here, which is going to have many subparts to it, is just different examples of the way these methods combine together, as well as some extra practice when the problems get a little bit trickier. So with that said, we've covered all of the methods, so try pausing the video now and see if you can completely factor parts A and B of example 7. Well, part A is probably the most straightforward of the problems we're going to take a look at, because that's just a formula. 8 is 2 cubed, so that's a difference of perfect cubes. So when we factor, it's going to be A2, A squared, then the product, 2 times A, 2 squared, so 4, and then for the signs, same, opposite, always positive. Now, you'll find that because of the nature of the difference in sum of perfect cubes, this quadratic that you end up with parentheses, it never factors further, so you don't have to worry about that. This is it. If it did factor further, that would be baked into the formula. Part B, on the other hand, is definitely trickier. So, no greatest common factor between all three terms. That's usually where you start each problem. That's not going to work here. Instead, the trick is to recognize that you've got the same variables, but with the exponents exactly twice as big. So from an a squared b to the fourth to an a to the fourth b to the eighth. So again, by property of exponents, a squared b to the fourth squared, exponents distribute across multiplication. So that would be a squared squared b to the fourth squared, which would be a to the fourth b to the eighth. So this is a 4 a squared b to the fourth squared minus 8 a squared b to the fourth minus 5. This is a quadratic type problem. So if we do a substitution, if we let u be a squared b to the fourth, this is a 4u squared minus 8u minus 5, and now we can factor it like a quadratic. So two numbers whose sum is a negative 8, and whose product is a times c, or negative 20 in this case. So the signs are different because the product is negative. We got a plus and a minus. And so two things that multiply to give 20 and subtract to give 8 would be a 10 and a 2. But since the 8 is negative, minus 10 plus 2. 2 probably pairs better with the 4. 10 probably pairs better with the 5. So I'm going to write this as 4u squared plus 2u minus 10u minus 5. Factor by grouping. If I pull a 2u out of the first two terms, that leaves me with 2u plus 1. And I want to get rid of the minus sign in these, so I'm going to factor out a minus 5 from the second 2, which would also leave me with 2u plus 1. Pull the 2u plus 1 out in common, which would leave us with 2u minus 5. So we're almost done. We just have one step left to go, and that is to reverse our substitution. So I'm going to replace the u with a squared b to the fourth. And once we make that substitution, nothing else will really simplify at that point. All right, so once again, try pausing the video and see if you can find the solutions to part C and D of example 7. So again, usually the first thing you try in each problem is greatest common factor. Just look for that. And we definitely have a greatest common factor in part C. So 3 divides into both of the numbers, and we also have an x in common between each. I usually like my highest power of x again to be positive, so it's not necessary, but I'm going to factor out a negative 3 from both terms as well as an x. So that would leave me with a positive x squared from the first term, and because I'm pulling out a negative 3, it's going to flip the sign, minus 9 from the second term. The x is gone because we factored it out. We're not quite done yet though, because this is now a difference of perfect squares. X squared minus 9 is x squared minus 3 squared. So we can factor that further into a plus b times a minus b, x plus 3 times x minus 3. And so the fully factored polynomial is a minus 3x times x plus 3 times x minus 3. Part D, again, you probably want to start by thinking about greatest common factor, but because you've got a term without any a's at all, and you've got a term without any 4's at all, no good. Instead, this is actually just a really straightforward factor by grouping problem. And you can really learn to spot those by noticing the commonalities between the first two terms and the second two terms. At the very least, it's something worth giving a shot. So for the first two terms, if we factor out an a squared in common, that would leave us with a plus 1. For the second two terms, factor out the minus 4 in common. That would also leave us with a plus 1. Factor out the a plus 1 in common. That would leave us with a squared minus 4, but once again, we have something that factors further. A squared minus 4 is a difference of perfect squares. So the a plus 1 carries over, but the a squared minus 4 is going to be a plus 2 times a minus 2. And let's do one last set, one more time. Try pausing the video here and see if you can completely factor parts E and F of example 7. All right, so for part E, again, you should probably start by checking for greatest common factor, which we have in this case. There's a's in both terms. So if we pull the a cubed out, that would leave us with 8a cubed in the first term and b cubed in the second term. We're not done though. This is actually a difference of perfect cubes. All right, because 8 is 2 cubed, and 2 cubed a cubed is 2a cubed. So we've got 2a cubed minus b cubed. So this a cubed is still going to sit out front, and then I'm going to factor. It's the first term, 2a, second term, b, first term squared, so 2a squared, which would be 4a squared. Then in the formula, it's ab next, so that's the product of the two. 2a times b. And again, you don't pull the minus sign into this. That's taken care of by soak in a second. So that would just be 2ab. And then the second thing squared, which would be b squared in this case. A little bit messy this time around because this first thing, 2a, is a little bit messy. And then for signs, soap. And again, this is a difference. I think we've already worked two differences at this point. Same, opposite, always positive. For part F, once again, there's nothing in common between all four terms here. You've got A's and D's in the first, but even in the second one, there are no A's, there are no D's. So there's nothing in common between all four terms. Instead, especially when you see four terms like this, That's a hint that factor by grouping is probably what you're looking for. So this is a factor by grouping problem, but I'm going to rearrange things again to make it match up. So this is going to be an a squared d. I'm going to move the a squared c up. So plus a squared c minus b squared d, and I'm going to move the minus b squared c to the end. And the reason why I did the b's in this order is to line up the d and the c with what I saw in the first two terms. But you could certainly rearrange that in a separate step if you don't catch that. So now in the first two terms, I have an a squared in common. So I can factor that out. And in the second two terms, I have a minus b squared in common. So I can factor that out, which leaves us with a positive d and a positive c. And then I can factor the d plus c in common out, which will leave me with a squared minus b squared, but that's a difference of perfect squares. So we can go a little bit further. D plus c, a plus b, a minus b. All right, and so that is it for section P5. In summary, the types of problems in this section is just factor polynomials. That's it. The difficulty of this section comes from the fact that we have a lot of different methods that we use to accomplish that goal. And you have to learn when each method is appropriate, and the more of these problems you work, the more patterns you'll start to spot. Greatest common factor is usually your initial go-to. Try that first. If there's something in common between all terms, factor by grouping, again, that usually happens specifically as part of the British method for ax squared plus bx plus c, or if you have a polynomial with 4 terms. That's probably a sign that you should at least check out factor by grouping. Then for quadratic polynomials, that's just a very procedural process that takes a little bit of practice. Special products know the formulas for the difference of perfect squares and the sums and difference of perfect cubes. And then we've got factor using substitution, which is where you take something that looks kind of like a quadratic polynomial and use substitution to make it look exactly like a quadratic polynomial. And of course, you can have problems that combine multiple of these methods together. All right, so as always, if you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.